Okay, any questions? Now we started with waves, linear waves. We said that, okay, here we have a linear wave. There are special kinds of waves, what we call harmonic waves. Now, what we call harmonic waves are waves that can be written as cosines or sines. X minus Vt, or sine k times x, but it can be plus or minus. Or you can obtain basically the same description as exponentials, e to the power plus or minus I k x plus or minus Vt. These are what we call harmonic waves. Well, for practical reasons, most of the time, working with complex representation is much easier. Now, of course, when you are working with complex representation, you should understand that it's the real part that is your actual wave, or the imaginary part that is your actual wave. Now, we will make several definitions over here. You see, here we have this k. K is what we call the wave vector. Now, if you look at these sines and cosines, well, they look like this. They just repeat themselves indefinitely. And as time moves, all this shape either moves towards the positive x or towards the negative x, depending on the sign between the x and the Vt term. Now, there is a length after which this pattern repeats itself. So you see, if you just sit over here and look your wave, or if you sit over here and look at your wave, you will basically see the same thing. So because at every distance L lambda in x, it just repeats the same pattern. So this length is what we call lambda. It is the wavelength. Of course, if this is the case, you see, if you shift x by lambda, the sine or cosine of this should be equal to sine or cosine, whichever one you are working with, of k x plus or minus Vt. And this is only possible if k times lambda is just 2 pi. Well, it is possible if k times lambda, that's the difference between this argument of this sign and this sign, that's the difference in k lambda. It should be a multiple of 2 pi times n. But since here the wavelength is defined such that it is the shortest distance after which the pattern repeats itself, then it's just 2 pi. So this wave vector k and the wavelength lambda, they are related through this relation. Another definition that we will need will be the frequency and the period and the angular frequency, which will all be related. Let's start with the period. Period is, for example, if this is a wave moving in the positive x direction, after a time capital T, it will move a distance lambda. Well, since the wave repeats itself at every distance lambda, at every shift lambda, well, basically after a time capital T, it will just look exactly the same. So that would mean that we have sine. Well, let me just stick with sine, but keep in mind that it can be the cosine, it can be the exponential representation. It doesn't really make any difference. K of x plus or minus v t plus capital T. This is how the wave will look like after a time capital T, starting from the time small t. This should be equal to sine of k x plus or minus vt. Again, the smallest time capital T satisfying this condition should satisfy kv times t should be equal to 2 pi, or t is equal to 2 pi over k times v. So this is after this much time, the wave starts to repeat itself. We have the inverse of this, basically meaning how many times the wave repeats itself per unit time. So we know that after this, let's say after 2 seconds, our wave repeats itself. So every second, it repeats itself well, it doesn't really make too much sense. Let's say if the period is 0.1 seconds, the wave repeats itself every 0.1 seconds. In 1 second, it repeats itself 10 times. So that is what we call the frequency. This is just 1 over t, or kv over 2 pi. Well, you see, if you look at the definition of our harmonic wave, we have the kx term and the kv term multiplying the time-dependent part. If you look at the kv term, it's 2 pi times the frequency. Well, this we call omega, which is called the angular frequency. Well, the sine and the argument of sine and the cosine is usually some kind of an angle, and the angle repeats once the cycle repeats itself, the angle changes by 2 pi. So if the frequency is 1, the angular frequency is 2 pi. The change in the angle is just 2 pi. That's why we call this angular frequency. Well, in most cases, there is no particular specific angle that we are talking about, but we can just make the analogy. For example, if you have, let's say, assume you have a circle, and there is a mass on this circle doing uniform circular motion. This is x, this is y. Let's say this is the angle theta. If it is doing circular motion, uniform circular motion, theta will be just omega t. So if you look at the x component, it's the radius times cosine omega t. Just like in our harmonic wave, if the harmonic wave is cosine kx plus or minus kv times t, this is cosine kx plus or minus omega t. For a fixed point, if x is constant, it is just cosine omega t with a phase, just like over there. So due to this analogy, we are calling this omega the angular frequency, although in general there is no angle we are talking about here. This is just the analogy. So let's look at this wave. So at t is equal to 0. No, this is x. At t is equal to 0, it will basically have this shape. This point over here is x0 is equal to minus delta over k. And this wave is moving in this direction. Now this delta is usually called the phase shift. So if you look at the cosine function has a maximum when its argument is 0. But in this case, it's not when x and w are 0. It is when delta was 0, the maximum will be at t equal to 0, the maximum will be at x is equal to 0. But if delta is non-zero, all this wave is kind of shifted in one direction. And the maximum doesn't arrive at t is equal to 0, but it arrives at a later time. So the maximum is delayed. So in a sense, this delta is also tells us how much the wave is delayed. So if delta is 0, it's not delayed. It is positive, it is delayed, meaning that the maximum arrives afterwards. Of course, this doesn't really make too much, it's not really unique. In one sense, delta for this exactly the same wave, this maximum didn't arrive yet at t equal to 0, but this maximum has already passed. So basically, you restrict the definition, the delta to, you can choose different values of delta. You choose the one that is between minus pi and pi. So that tells you that the delta over here, this is delayed because this is the closest one, not that one. Now, of course, these harmonic waves are, there are special kinds of waves. Not all the waves, in fact, very rarely you get a harmonic wave. Well, very rarely, even that is kind of an exaggeration. You never get a harmonic wave. But whatever the wave you have, you can always write that wave as a linear superposition of these sines and cosines. That's what the Fourier tells us. So whatever your wave is, I can always write this as some kind of e to the power I kx minus omega t. The k from minus infinity to plus infinity times some function, let's say of k. Well, in general, in this case at least, I'm assuming that k and omega are related with each other. They are not independent, so that's why I only have a summation over k. Well, since this is always satisfied, we can always write this one. If this is a solution of our wave equation, integral is nothing but the sum of these solutions. But if our medium is medium, the sum is also a solution. So if we can show that if we can know how to manipulate these plane waves, basically it allows us to extract information about any wave in our medium. So that's why we are specializing on these plane waves, on these harmonic waves. Now, of course, this was an example in one dimension. We can say that, okay, this example will also hold for a wave that moves only in one direction, let's say only in the x direction, and the amplitude doesn't depend on y or z. In general, we can write a three-dimensional vectors for minus infinity to infinity. No, not minus, let me say. This time k becomes a wave vector. Okay, here, well, that's why I called it a wave vector. In one dimension, it's usually called wave number. But in three dimensions, it just becomes a vector. So it's e to power I k dot r minus omega t. Now, sometimes you put 2 pi's in the k integral, sometimes you put 2 pi's somewhere else, etc. That's just a matter of convention. So in fact, this is why we are specializing through the sines and cosines only.
Signal processing konusu sanırım ama mesela bu deneylerde şeyi nasıl ayırıyorlar? Test-Fourier transform algoritmaları var herhalde ama bir dağdan yani onun içinde evet hani bu da belli dağların farklı kombinasyonları odağlanıyor oluşturmuş ama unik bir kombinasyon var mı? Yoksa unik bir kombinasyon olamaz sanırım. Değil mi? Var mı?
Well, let's see. Let's just review some of your knowledge about Fourier analysis. Okay, so this is the Fourier integral. You can invert it. If you know your function f, then g of k is nothing but, well, d cube r, let me say d cube k d omega. Let me add the omega. And then this k will depend on omega for simplicity. Now, of course, this gk of omega function might be 0 unless omega and k, they are related somehow. So that will be imposed by some Dirac delta functions, for example. So if this is the case, then this gk omega will be equal to d cube r e to power minus I k dot r minus omega t, f of r of t divided by 2 pi cube, 2 pi to the 4. Well, again, as I said, depending on your convention, this 2 pi to the 4 sometimes it appears in this integral, sometimes it appears in this integral. The important thing is whatever you are dividing this d cube k d omega, if you multiply that with whatever you are dividing this d cubed r dt, their product should be 2 pi to the 4. But you can just split it in symmetric wave, unsymmetric wave, etc. Is this integral unique? Yeah, this is unique. This is a unique representation of my function. But let's look at this one. How can we determine this function? Here we have an integral over time, from minus infinity to infinity. Furthermore, we are having an integral over space from minus infinity to infinity. Well, we never can evaluate this integral, neither this integral. We can never do this practically. This means that our wave should exist from minus infinity to infinity. It should be created at this imposition. If it's created at the eternity in the past, it should exist until the eternity in the future. We should be knowing all of that, and we should be knowing its value at infinity in that direction, infinity in that direction, etc. That never happens. In practical terms, what happens is we create the wave in this volume. Let's just imagine in space and time. We create it at some time, and after that time, we just unplug the device. So there's no more wave created. And that wave, when we create it, is localized in this region. And again, if you go back to your Fourier analysis courses, rather than working with all these position and the time dimensions, let's just take one-dimensional example. Forget about the time, forget about the position. What do we know about Fourier analysis? Suppose you have this function as a function of, let's say, x. It has some weird shape in some finite interval, f of x. So you know this function in this interval. And what you care is that you just want to find the Fourier series, or a Fourier integral, Fourier series, let's say, that matches my function in this interval. So what I can do, again, just for simplicity, let's assume that I have a 0 over there, and that is at x equal to 0 point. Again, just for simplicity, just for the sake of making the argument clearer. Since it is 0 over there, I can make a sine series of this function, and then this function f of x will be equal to some sum from n is equal to 0 to infinity, or 1 to infinity, sine of n pi over L x with certain coefficients. So this is one possible representation of my function within that interval. But of course, if you calculate this function out of that interval, well, here I will have something else. It will repeat itself over here, repeat again. So it just repeats, but I don't really care because in this interval it matches. Well, I can also write it as I don't have to write it as a sine series, I can write it as a cosine series also. Although it is 0 at that point, f of x will be equal to sum over n. The only critical part is that I have to take the odd terms, because the odd terms are 0 at x is equal to 0. Right? No, I cannot. Yeah, I can write it as a cosine series. No. Or yes. I should be. Okay, some cosines, some bn, I can write it as a cosine series. But this time, when it repeats itself out of my domain, it will not go down. It will go up. So I cannot write this as a cosine series. At x is equal to 0, it will always be 1. No, I can. It will be complicated to write it as a cosine series. Let me put it this way. No cosine series. I can consider it as such a function, and I should be able to write it as a cosine series also. Yeah. Okay, it does exist as a cosine series. This is a different Fourier series for exactly the same function. L prime is somewhere over here, let's say. This is another sine series. And the third function matches my function in this region. It is 0 here, and then repeats itself. So in this, since we are talking about a finite expression, the series expansion is not unique. So there we have these ambiguities, of course. Now another problem, especially when you are talking about, you have taken quantum physics, right? Yeah. Okay, so you will be talking about the uncertainty principle. Now when we create harmonic waves, so there we have our device that creates harmonic waves. So what do? We just, at some given time, we just turn it on. And the waves are propagating. They look like harmonic. And at some time, it can be a long time, but eventually the device breaks down or we just turn it off. It looks almost harmonic. So let's say this is x. We can talk about its Fourier transform or Fourier series. Just imagine that for this time we are saying that, okay, before we switch on the device back until eternity in the past, there is no wave. So we know its value. It's 0. When we turn on the device, we are creating this almost harmonic waves. And then after some time, we turn it off. So after that point, there is no harmonic wave whatsoever. Well, if you take the Fourier transform or look at the spectrum, X or T, whichever one you like. And you can say that either that is the how the wave looks at a later time, T, or you can say that you are just measuring the wave at this point, X, and it will be oscillating up and down. You take its Fourier transform. What does it look like? Well, you just created a given frequency. You would expect just a single point on this graph. But actually, it's not a single point. So you have this shape. This is the frequency that you thought you were creating. The device was designed to create a wave of frequency omega 0. But since it only lasted a finite amount of time, it cannot create just a single frequency. There's a spread of frequencies. And the longer this becomes, let's call this T. Let's call this delta W. Delta W times T is fixed. Or you can just call this delta X. Then this one will be delta K. Delta K times delta X is fixed. If you want a single frequency, then your signal should last infinitely long. T should be infinite. If delta W is 0, T should be infinite. If you cannot create infinite duration wave signals, you cannot create a single wave. Or similarly, if you want a single wave vector, then if you want delta K to be 0, then your wave should be infinitely long. This is a property of the wave phenomena. And in fact, this is what's called the uncertainty principle in quantum physics or quantum mechanics when you see it. So once you start describing your systems as a wave, this uncertainty is unavoidable. I don't know if it has been an answer to your question. Probably you have heard of all these phenomena. They were claiming that there is superluminal signals. There is this nonlinear medium that the signal you send appears from the other side before it enters the medium, etc. The problem there all the time is some confusion with this concept of superposition. So since you are all the time creating a superposition, your signal, no matter what you are creating, even if you think that you are sending a given frequency, it's always a superposition of different waves. And these superpositions can behave weirdly. Weirdly in the sense that you create some superposition over here, some signal. As it evolves, some signal might appear over here. Although this bump never went from this point to this point, the bump over here disappears, it might appear from here. But that's basically because of this superposition principle. You have to first create all the frequencies that are relevant in your signal, and that, what's called the wave front, should have already reached the other side, and then the peaks might appear to have moved at speeds larger than the speed of light. It's just the appearance, though. Okay. I would rather avoid that question for the time being. Have you met Emre Yüce? He has a lab in the entrance floor close to the small elevator. He has a lab over there. He once gave a seminar on that. He's also working on those things. Ask him. He knows more details than me. So you will also meet him. Okay, so this is how we describe, or the terminology that we will use when we are talking about waves. We will be talking about their wave vectors, wave numbers, frequency, angular frequency, period, etc. And we will be most of the time dealing with harmonic waves because, one, they are easy to work with. Second, as long as we are dealing with linear phenomena, any wave can be written in terms of these harmonic waves. So it's not really a restriction on the applicability of our results. Our results will be valid for everything. Now let's look at, okay, so this is nice, this is how we will describe it, but most of the time what we do in physics is you study your system, you have some differential equations describing our system. So the question is, what kind of differential equations should we derive to be able to say that a given system has some wave-like solutions? Now, we said that this is the general solution. Now, where is it? Now, this is the general solution of a wave. Now, let's see what kind of a differential equation does this solution satisfy. Now, it depends on x and t. Let me take some derivatives with respect to x and t. This will be g prime at x minus vt plus h prime x plus vt. Well, to describe the wave phenomena, I'm kind of trying to relate the x derivative, time derivatives and position derivatives. That's what I will be trying to what I'm looking for. Is there a relation between the x derivatives and the time derivatives of f? Well, I took the x derivatives. In the x derivative, only the first derivatives of the functions g and h appear. You see, this g prime is not the derivative of g with respect to x. G prime is the derivative, this is the value of the derivative of this function with respect to all of its argument evaluated at this point. So it's not with respect to x, it's not with respect to t, etc. This g prime x minus vt is equal to dg by dy evaluated at y is equal to x minus vt. And since g has a single argument, I'm just calling that argument y in this definition. And then just using the chain rule. Derivative of g with gy with respect to x is that the derivative of g with respect to y multiplied by the derivative of y with respect to x, where y is equal to x minus vt. So this is equal to g prime at x minus vt. Derivative of x minus vt with respect to x is just 1. So that's how I obtain this relation. Let me look at the derivative of f with respect to t. I will just use the same reasoning, but just keep in mind that here, instead of x, I'm taking the derivative with respect to t. Derivative of y with respect to t is minus v in the first term, and plus v in the second term. Minus v g prime x minus vt plus v h prime x plus vt. Well, these two derivatives don't look related for a general g and h. Because here, in the derivative with respect to x, the sum of the derivatives of g and h appear. Here is the difference of the derivatives of g and h. But I can cure that. Let me just take the second derivatives. df by dt del squared f by dt squared. This is equal to minus v squared g double prime x minus vt plus v squared h double prime x plus vt, or this is v squared times g double prime plus h double prime. I can take the second derivative of f with respect to x squared. This will be just g double prime plus h double prime. But this is nothing but 1 over v squared, second derivative of f with respect to t squared. So this is our wave equation. Del squared f by del x squared minus 1 over v squared del squared f by del t squared, this is equal to 0. This is in 1 dimension. Well, we will be dealing with 3 dimensions in general. So the second derivative in 3 dimensions is nothing but our Laplacian. So this tells me that if something satisfies this equation, in our case it will be the electric and magnetic fields. We will show that the components of the electric and magnetic field, they satisfy this equation. So this tells me that there are waves corresponding in that system. Well, let's look at one example of a wave phenomena, how it comes from the underlying physics. Let's look at the waves on a string. So what do you do to create waves on the string? You pluck this, you stretch the string, then you just deform it somehow. That's your initial condition. Then once you release it, its evolution gives you the waves. So let's look at, we have this string stretched. There is a tension T on the string. Now as you just release it, it will be evolving with its own dynamics. Once you pluck it, you release it, it will be evolving in its dynamics. So let's see what are the equations governing its time evolution. So this is the unplugged string. There are no waves on it. Let's assume that at a given instant, it has this form. Some arbitrary shape. I mean, it doesn't really have to have this shape. Now we know Newton's dynamics. Let's look at one part of this string. Let's look at this part. Well, that part has some mass. It corresponds to some length. Let's say called dx, and it has a mass dm. And we will assume that we don't really deform the string so much. So the tension doesn't really change. It's more or less constant at every point. Because of course, if you just deform it significantly, then the tension from point to point will change. But if your deformation is very small, the change in the tension will be quite small. Let's say this is our x-axis, this is the y-axis. Now, what does Newton's law tell me? That the acceleration of this very small mass, d squared y by dt squared, let me write it in this form. Y is not just the deformation of this small mass, but it is the deviation from the equilibrium at the point x at the time t. So if that point, that small mass m is at the point x0, just put x0 over there, that is fixed. I take its second derivative with respect to this argument only, the time, and that gives me the acceleration of that very small mass. Yeah. Well, this is the acceleration. It should be equal to, if we multiply acceleration with mass, it should be equal to the total force acting on it. Well, let's see, what about the force? There is a force from here, pulling it in this direction due to the tension. There is a force at this point pulling it in this direction. The tension will be parallel. Now, the tension will be parallel to the string, but since there is some length, dx, between this point and this point, those two forces, they are not anti-parallel. Let me just exaggerate that picture a bit so that we will see it easier. Let's assume that this is the part of that string over there. Now, at this point, the tension is in this direction. At this point, the tension is in this direction. Both are T. Now, I'm just looking at the y component of the force. So the total force, the y component of the total force, will be, let me say, this is the point x, this is the point x plus dx. This is the, this is dx. This is the angle that T makes with the horizontal at the point x plus dx. And this is the angle it makes at the point x. So the y component of the total force, it will be a small force, will be T times sine theta plus x plus d, theta evaluated at x plus dx minus T times sine of theta of x. I will make one more assumption. I will assume that theta is small. So, I mean, the deviations from the horizontal are, I didn't pluck it very hard, so the deviations will also be very small. If the deviations are small, sine of theta is almost tangent of theta. Well, tangent of theta is the slope of the tangent to my string, but the slope of the tangent to my string is nothing but dy by dx. Or since y depends on both x and t, it is the derivative of y with respect to x. Of course, evaluated at whatever your x point is. Now let's go back. dm times d squared by dt squared y of x of t. This is equal to t times del y by del x evaluated at x plus dx minus del y by del x evaluated at x. Because here I have the angle at the point x plus dx, here I have the angle at the point x. So those are the slopes at two different points. Let me divide this thing by dx and multiply by dx. Well, you see, forget about that, this function being dy by dx. This is just some function. We don't know this form, but it's just some function. We are evaluating this function at the point x plus dx. We are evaluating the same function at the point x, subtracting them, dividing it by their difference. But this is nothing but the definition of the derivative of a function. So the function that we are talking about is already the derivative of y with respect to x, the first derivative. This is nothing but the second derivative. So this is equal to t times dx times del squared y by del x squared. This is dm del squared by del t squared y is equal to this one. Or now let's organize it a bit. Del squared y by del x squared minus del squared y by del t squared 1 over t over dm by dx. This is equal to 0. Well, dm was the mass of the length del dx of my string. So dm by dx is nothing but the length the mass per unit length. So if you write v squared as t over lambda, then del squared y by del x squared minus 1 over v squared del squared y by del t squared is equal to 0. Well, this basically tells me that there are waves. I can create waves on my string, and those waves, they will have the same velocity. They will all have the velocity given by the tension and the mass density. Also, when we are looking at the electromagnetic fields, our strategy will basically be more or less like this. We will be trying to relate the second derivatives with respect to the position to the second derivatives with respect to time. And once we obtain such a relation, we can see what the velocity of the wave is, whether that velocity will be the same for all frequencies or whether it will be different for different frequencies, etc. And then the next step will be, well, we have the waves, what about boundaries? You see, in our first semester, we had studied how the electric field and magnetic fields change across a boundary. Well, on Friday, we will just pick up from here. So we have the waves on a string. We will just try to analyze what happens if you just tie two strings together and send one wave towards the other string. So will it be reflected? Will it be transmitted? Because the things that we will use there, we will use exactly the same thing when we are studying electromagnetic waves. And then it will be important to identify the boundary conditions. What will be the boundary conditions in our system? How we can determine the boundary conditions in our system. Okay, any last minute questions?
Hocam şuradan DX'e çarpıp DX'e bakınca şu
Okay.
şeyi yazdı.
Second derivative.
Onu nasıl yazdı?
Well, let me write it in this form first. You see, here I have a function, or here I have a function. I evaluate it at some point. Here I have the same function. I evaluated it at a point very close to the first point. Eventually, their difference will be just 0. And I divide by their distance. But this is the definition of the derivative. The derivative of a function is just calculate its value at that point, calculate its value at a very nearby point, look at the difference, divide by the separation between those 2 points, and take the limit as that separation goes to 0. That is how we define the derivative. So this ratio in the limit as dx goes to 0 is nothing but the derivative of this function. It's the derivative of that function. You have one function, take its derivative with respect to x, take its derivative again with respect to x. That is our second derivative. Now, just because I saw this already, I'm just looking at the difference of the value of a function at 2 very nearby points. You can just realize that it's the derivative, almost. The only thing missing is dividing by the distance between those 2 points. But I can always add that as long as I also multiply that. Divide by that, multiply by that distance, nothing changes. And then I can identify the second derivative. So see you on Wednesday. Who wants a recitation this Wednesday? Okay, enough people. We will have a recitation.